Hello, in today's video we're going to use technology to solve some problems with logarithmic and exponential equations. Now we have technology available to the public. You can pay a little extra at many different websites. Wolfram Alpha is a great resource for mathematics and other students. Why do we need to learn how to actually do the techniques since we have the technology is a common question, and that's a rational question where if you're a calculus student, why do you need to learn how to integrate sine x cosine x squared when you can just go to one of these websites or plug it into a graphing calculator and get step-by-step solutions? Why do you need to know how to do these steps if they can be done for you by a computer? Well, for one, we don't want the computers to take over the world, and so we have to make ourselves competitive with our robot friends, or else they'll become our overlords. I jest, of course. Another reason is we need to know whether you're a student. If you're a student, then you have to know how to do these things on the test without technology, for one. But even if you're in the working world, if you don't have that base knowledge of what these techniques are, what these mathematical processes mean, then you won't be able to understand how to solve the problems if you're an engineer or a scientist or somebody who is in finance or even in just your daily life. Mathematics is in fact everywhere. And so having a good understanding of what these techniques and processes are will actually give you a better understanding, a deeper understanding of the world around you. Even though the details, as I say, you can go to Wolfram Alpha and figure out any number of different very complicated linear algebra problems or calculus problems step by step. The machine will do it much faster, much more precisely and accurately. So sure, we should use technology, but we also need to know how to do these things. Maybe we don't need to know how to do the most difficult problems in the world, and certainly it's faster using technology. But we need to know if the technology is right or wrong, have a good basic idea of, well, what technique do we need to use, etc. Right? So I've pulled up several problems from a pre-calculus book. This one, first one, says model population of a certain country from 1999 was 287 million people. In addition, the population of the country was growing at a rate of 1% per year. Assuming that this growth rate continues, the model P of t, that's the population over time, is equal to 287 times 1.01 raised to the power of t minus 1999. And that's the population P in millions of people in the year t. Now, they came up with this equation here by using the data and finding this equation by interpolating or extrapolating. They're reading into the data or they're pulling something out of the data. Right? So what we are going to do is look at A. So I've got Geogebra here. Everybody can download this for free. I plug the function in. Here's our function. So from year 0, we're looking at this part of the graph over here. You can zoom in. I've even got the letters A and B here already plotted out for us. According to this model, when will the population of each country reach 307 million people? And so 307 million I've got right here as A, and so I put a point using GeoGebra. Had to recalibrate the units and the scale on the x and y axes so that we could get a precise answer. And so our point there is 307 million, and that's in the year 2005. Next question, according to this model, when will the population of the country reach 394 million? Let's zoom out. Got point B. And again, I've zoomed in and done the heavy lifting, so to speak, even though it was really quite simple, just adjusting the point around using this function here. Point B, 394 million, right, on the y-axis, right? So y, the population is dependent on the time, right? So in the year 2030, near to the end of the year 2030, they'll reach 394 million. Next question. Depreciation of an automobile. So we're seeing that these exponential and logarithmic equations can have some value in our real lives. The value v of a certain automobile that is t years old can be modeled by the equation v of t, the value as a function of time, is equal to $14,162 times 0.83 raised to the t. Right, this t is time. According to the model, when will the car be worth $8,000? This is depreciation, so we're going downwards. Of course, everybody knows you buy a car, and as soon as you drive it off the lot, it depreciates in value. So I've got the function here. We're starting at year 0 is 14,162. I suppose that was new. Looking at this car, it was probably new. $8,000, that's point A. That is in year 3, the beginning of year 3. Letter B. According to the model, when will the car be worth $3,000? Well, again, we get these models by taking a lot of data, millions and millions and millions of points, or at least hundreds of thousands of points, and then they'll use technology. It's much, much faster than doing it all by hand. We could do it by hand and find this logarithmic or exponential decay model here, but it is much faster to use technology like SPSS. By plotting a number of different points, and then SPSS or some similar program will find the line of best fit, or the formula, the function of best fit. So at $3,000 on the y-axis, value is a function of time. Right, here's our independent variable x, that's time, and then y moves up and down depending on time. So in year 8, about a third of the way through year 8, we get to $3,000. And then $1,000, we're at year 14. So after 14 years, it's worth only $1,000. Right? These were very simple, very easy to graph out. Right? So again, technology can really help us to increase our productivity. It helps us do things faster. And it increases our accuracy in mathematical equations. So we can do it faster, and we can do it more accurately. We won't make as many mistakes with technology. Comparing IRA investments. Trish invests $6,000 in an IRA in a bond trust that pays 8% interest compounded semi-annually. Sean invests $6,000, same amount, in his IRA in a certificate of deposit that pays 7.9% compounded continuously. Well, semi-annually means twice a year, so the interest comes through twice a year. Compounded continuously means every moment of every day that 7.9% is growing and growing. Who has more money after 20 years? Well, for those of you who know anything about finance, you'll know that continuous compounding results in slightly higher future value. But here are our formulas. The amount A after t years is t years due to a principal P. Here's our principal P, that's the amount we invest. Here's the future value after t years. And we've got our interest rate R divided by N. If we're compounding semi-annually, N is 2 because that's twice a year. 1 plus R over N raised to the power of NT. Again, N is the number of times per year, and T is the number of years. In this case, X is going to substitute for T. All right, so our first equation looks very much like this. You can't see all of it. Raised to 2x. 6,000 times the quantity 1 plus 0.08, that's our percent interest, over 2, raised to the power of 2x. This is a very high rate of interest. We're probably not going to see that again for a very long time. I don't know where these people are getting their IRA investments. Certainly a certificate of deposit at 0.79. Oh, sorry, this should be 0.79. 0.79. And so, after 20 years, we can see that, yes, PE to the RT is slightly higher. The continuous compounding is slightly higher. It has $29,129. On an initial investment of $6,000 after only 20 years, that's pretty good. $28,806 for the bond is also pretty good. 8% is a great interest rate for such a relatively low-risk investment. Last equation, last problem here. We are looking at The Challenger disaster. For those of you who don't know, the Challenger was a space shuttle that exploded in 1986. The study was made of 23 launches that preceded the fatal flight. Precede means come before. The mathematical model was developed involving the relationship between the Fahrenheit temperature X around the O-rings and the number of Y eroded or leaky primary O-rings. Quick background here. The Challenger disaster, the space shuttle blew up because the launch, I believe the temperature in the morning of the launch was too low, and a business or an organizational phenomenon called groupthink happened, where one or a very small group of engineers raised protest and said that they should not launch because of the O-rings having shrunk due to the temperature outside, but there was too much pressure from the majority or all of the other engineers and people involved in the launch. So the majority ruled, despite the legitimate concerns that the low temperature could cause these O-rings to shrink, allowing some fuel to slip by, which in fact did happen. And so this case is very important even in business schools, where the group makes a bad decision for reasons not related to science. Right, so anyway, I have graphed out this equation here. We've got f of x, or the number of faulty O-rings as a function of the temperature, is equal to 6. There are 6 primary O-rings. That's along the body of the fuel rocket, or the fuel tank on the rockets. 6 divided by 1 plus e to the negative 5.085 minus 0.1156x, just as it says here. So what is the predicted number of eroded or leaky primary O-rings at a temperature of 100 degrees Fahrenheit? That number is 0.001. Well, that's 0. At 60 degrees Fahrenheit, again, we're going to say that number is close enough to 0. I believe this might be the minimum temperature. This is very near the minimum temperature for launch because of this very problem. Right, so that's 60 degrees. What's the number at 30 degrees? Got C is right next to D3. You can't really see it. At 30 degrees, 5.01, and so nearly 6, or over 5 would be 6. So the part D here says graph it out. We've been looking at using graphs to solve these equations, to solve these problems. And so what temperature is the predicted number of eroded or leaky O-rings? An O-ring is like a rubber washer, basically. It stops fluid passing by. Everybody's got one in their sink. You can unscrew the tap and find an O-ring in there. You've got one in your garden hose. A lot of plumbing uses them. So 1, 3, and 5, and so here 5 O-rings are defective or leaky because they shrunk at just over 30 degrees. 4 O-rings are leaky or shrunk at 37.99 degrees. 3 O-rings are leaky or defective at 43.99 degrees. And if we wanted to find, let's see, 3 and 5, we've got 3, 1. If we want to find where is 1, well, that's very close to B, but let's zoom in. All right, and we're going to choose a point here that looks like about 1 on the y-axis, and bang, we got it. 57.91 degrees for 1 leaky O-ring. But even just 1 leaky O-ring will do it, and it could result in a major explosion and the loss of several people's lives, a lot of work, and more or less representing some sort of disaster in the way that people think. Right? So we can't ignore the data. If we've got this data, then we have to use it. It doesn't matter what political or business concerns we have. We must, in fact, ensure safety of the astronauts and of all the people involved by not launching at what looks like less than around 60-some degrees. All right, so again, using technology can definitely help us speed up our mathematical processing. It can help us to understand it better, and you can go to Wolfram and get step-by-step solutions so you can help your homework, help you learn how to do these things. And we need to still learn them because we need to know if we're in roughly the right ballpark with this type of stuff. And then also because we can't let the machines and robots take over the world and take all of our jobs. And so we need to at least be a little bit competitive. All right, thank you.